So after we discussed uh, divergence and gradient, now it's your turn. Your turn is to discuss the curl of a vector. So we will define what is a curl now. Curl is basically the rotational, or simply it can be said the rotation of a particular vector, which is defined by curl. So let us now see what are the few properties and characteristics of this curl of a vector. Now first, it gives it gives measure of circulation of a vector field, that is how much a vector can rotate or twist or curl around a point. That is, if you are having a point like this and you are having a vector from this point as say vector f, so it will curl will measure how much this vector can rotation. It will measure of the rotation. Suppose from here one some position a, it has come to position b, so this angle will measure the curl of the uh, this vector field fx from position a to position b, right? So the next characteristic that will be the denoted is this, generally the curl is denoted by curl of vector f, or simply this is cross product del cross f, right? So in case of, remember, we have to remember this, for gradient we have del f, or not dot, del f. For divergence we have del dot f. For curl we have del cross f. These are the three different types of notation that we have. Okay, so now the next property is that these are curl is defined as maximum rotation of any vector f per unit area, as this area tends to 0 and its direction is normal to the area, right? So that means we can define this curl of any vector f, that is defined by limit del of s tends to 0, line integral of f. Since this is a line, this vector will rotate, so we will simply use this as a line integral f dl by, throughout the surface it can rotate, so we're taking this del of s to unit vector an. This is the definition and general properties of a curl of vector. Next we will discuss the effectivity of this curl of a vector, or what do we mean by this curl of a vector mathematically. We will try to prove it. Okay, so here we will discuss the mathematical expression of curl of a vector. We'll simply analyze mathematically what is exactly mean by the term curl of a vector. So for that we have drawn a simple diagram in xyz plane, where we have considered an elemental area in yz plane. This is an elemental area in yz plane, and let p at the point p be a vector at the center of the area. I mean, if this area is encircled by a b c d, and within this area there is a point which is p, or point, or rather it is a vector which is enclosed, which is at the center of the surface that is enclosed by a b c and d, right? So we will consider, so simply we will write, consider an elemental area, as I said, elemental area on yz plane, right? Next, let p be a vector at center of that area, as I said, center of that of that area in the yz plane that we have drawn. Okay, so now closed line integral, we will discuss the closed line integral. I mean, our job is to see if this point is p is a vector quantity and it rotates like this throughout the area, like this, for say from a to b, from c and d, like this. It actually rotates like this. We are going to measure the how much rotation, or how to define that this is the curl of this vector p throughout the surface S that is enclosed by a, b, c and d. Okay, so now the closed line integral along a, b, c, d, so we can write now closed line integral along a, b, c, d, that is by this area or surface area. We can write this is a closed line integral of f dl. So this we know that this represents the closed line integral, since this surface is a closed one and this is a line, of course. So we'll represent by this closed surface line integral of f dl, that will be equals to the sum of d to a f dl from d to a f dl plus then a to b from d to a to b, b to c and c to d. So that is, we write one by one, f of dl plus now b to c, f of dl plus c to d, now c to d, f of dl. So this is the expression for closed line integral of this vector f, right? Now we will discuss, or we will evaluate one by one what will be the values of this line integral from a to b, b to c, c to d and d to a, right? So let us first discuss this one, or rather now from d to a f dl, this is equals to what? This is the component vector of f in y direction minus del of fy del z to del z by 2 del y. Now why this is so? This is vector, this fy vector, since we are talking about d to a, that is from d to a, this is in the direction of this vector in the direction of y. So we have written the function in terms of y here, and minus this is smaller element of del fy to del z. So why this smaller element of del fy fz? Because the y position is changing from y1, say I have written it here, y1 to y2 actually. So if this position is very small, this del y, smaller change in position, we can simply write this as del z of f in y direction, simply. That is why I have written it. So now, and that is of course in the direction of del y, right? Now del z is actually this one, so we have taken the half of del z in the direction of z1, z axis. So similarly we have write from a to b, f of dl will simply calculate fy plus del fz del y. Similarly you can write, so del y by 2 del z, right? Now let us calculate the other two also. Again this one, next one will be from b to c, from b to c it will be f dl, this is equals to minus y, because this, if this is the positive direction, this will be the reverse direction. So we will write this minus this fy minus del of fy del z by 2 del of y. So the next one remains. So you take a note of this, you can come back. So I am omitting it and writing the next expression. So the last expression will be del of from c to d, that will be f dl equals to, again minus, because it's in reverse direction from a to b. So we will write f dl equal to minus of fz minus d of fz by del y by 2, right, of del z. So these three equations we have got. So four equations, I would say that for all these values of the a, this one from d to a to b, b to c, and c to d, four equation expressions we have obtained. Now we will simply add these four expressions. So therefore in different components, right? So for x component, therefore x component of curve, since the area, why this we are getting the x component, since the area is in y and z plane. Okay, so we are taking the x component here from this component because the area is in yz plane, right? So correspondingly, if this becomes in xz plane, we will take the y1. So similarly, it changes as per the system or as per the locus of the system in the coordinate system, right? So we will simply write curl of f in x direction, of course, that will be given as limit del s tends to 0, surface integral of f dl by del y del z, that is equals to, or I can rather say this is equal to del fz del y minus del fy del z. So from here you can similarly say this one. So we will similarly in y and direction, this is the representation of the curl of vector x in only x direction, right? So we will find out in y and z direction. I am omitting it. So similarly you can write curl of in y direction of vector f equals to del of fx del z minus del of fz by del x, and curl of f vector in direction of z, that is equal to del of fy del x minus del fx del y del y. Okay, so now considering, so in x direction we have evaluated, then we have evaluated in y direction, we have evaluated in z direction. So we will simply add these functions. So considering all these three direction, or I would write it, considering all three directions, I will write curl of vector f is equals to del cross f vector is equals to addition of all, that is del, previously we have got del fz del y minus del fy del z, unit vector axy, this is because in x direction previously it was, and then here this one del fx del z minus del fz del x in ay, and plus del fy del x minus del fx del y to az. So this is your expression for this vector, or the curl of a vector f if of this total surface. This is your final expression, and hence the mathematical expression for curl of a vector. Okay, so finally we have come to the properties of the curl after discussion related to what curl is and their mathematical expressions. So we'll simply write the properties of curl of a vector. The properties are, it is important and these are need to be remembered. Result of curl of a vector is another vector, that is, if you do curl of a vector, it will result to another vector. Okay, another vector field. So, and the next one is, next property is curl of any scalar quantity has no meaning. That means you cannot do curl of a scalar quantity and the result will be nothing. Okay, so next, the last property, if curl of a vector is 0, it is known as, or it is called irrotational or conservative field, that is electrostatic field. This is an example where you have already learned about what electrostatic fields are. In fields which are static at a place, or rather it is not in a moving conditions. So if we do a curl of a vector, if it is zero, it is called a irrotational or conservative field, that is electrofield. So what it means, that if you ever come across the term of electrostatic field, which will of course we will get in be acquainted with in our future classes. So if this is, we are talking about electrostatic field, so it is obviously a conservative field or a rotational field, since it is a static one. But not, this is not the case in case of a dynamic field, which is I mean, if we do a curl of vector of a dynamic field, electrodynamic field, so it will never be zero, it will have some finite angular values, right? Okay.